Good morning to everyone. In the last videos, I already explained to you about the very basics of electronic spectroscopy and what are the types of electronic transitions possible in electronic spectroscopy, that is sigma to sigma star, pi to pi star, n to sigma star and n to pi star. And then we saw about the concept of chromophore, means when any oxochrome is connected to the double bonded one, its lambda max value may shift towards the right side, called as bathochromic shift, or may shift towards the left side, called as hypsochromic shift. Already we saw that. Okay, now I'm going to explain about this chromophore concept by taking conjugated dienes as an example. Okay, so you know that if you took only ethylene, its lambda max value will occur at 170 millimicrons. Okay, but if you add two CH3s, CH3 is added to left carbon, CH3 is added to right side carbon. In such conditions, what we will observe about the lambda max values? We will observe the lambda max values will shift towards the right side. That is, lambda max value will occur at 217 millimicrons. If you took 135 hexatriene, here this is not this one. What I want to say is single bond, this one, that is 1,3-butadiene. If you took 135 hexatriene, the lambda max value will occur at 254 millimicrons. Now we need to check how these lambda max values are shifting from left to right. So before telling about that lambda max shift, first we will see the ground state configurations of these two ethylenes. This is the ground state of first ethylene. This is the ground state of second ethylene. Okay. Because in ethylene we have one pi bond. That is, there are two pi electrons represented like this. Here also there are two pi electrons represented like this. We know from molecular orbital theory, when two are combined, we will get two possible ways. One is psi 1 and one is psi 2. Okay, means these two ethylenes can combine in two ways. This is obtained by the addition of pi plus pi. This will obtain by the addition of pi minus pi. Okay, right. Because there are four altogether, we arranged the four electrons like this. Now let us suppose this is the increase of energy. Okay, now this is the ground state of ethylene. So now I am writing the excited state of ethylene, that is pi star of ethylene. Now this is also pi star of the second ethylene. When these two are combined, we will get two different varieties. One is called psi 3, second one is called psi 4. How this psi 3 we will get? By the addition of pi star with pi star. How we will get this psi 4? By the addition of pi star minus pi star. Okay. So these are the types of electronic excitations which are possible in conjugated dienes. Okay. So for this what is that? In-depth explanation. For the in-depth explanation, we are taking the help of the concept of pericyclic reactions. Okay. According to this wave theory, the pi electrons is always represented like this. The pi electrons is always represented like this. This is called representation of pi bonding orbitals. Next, this is plus, minus, minus, plus. This is the way of the representation of anti-bonding orbitals. This is pi bonding. General representation of this pi bonding as well as pi star anti-bonding orbitals according to wave theory. Now we will see these possibilities one by one. How we got this psi 1? Psi 1 we obtained by the addition of pi with pi. So what is this first pi? This is the first pi, that is plus, minus, plus, minus. What is the second pi? Plus, minus, plus, minus. So now when these two ethylenes are combined, what is the possible way to get a bond? These two ready to make a bond, these two are ready to make a bond, and these two are ready to make a bond. Okay, so if you observe the bond like this is C1, C2, C3, C4. Happily these are mixed together, ready to make a bond. Okay, so which says that there is no nodal plane. Next one is what? Psi 2, that is pi minus pi. First I will write about pi, that is plus, minus, plus, minus. What about this minus pi? Minus pi means you need to change the symbols. Just plus minus unnayi kada, you need to reverse them. Okay, so it will become minus, plus, minus, plus. Okay, always we know the same charges will bind together. These two will bind together. Here there is no bond forms between these two. Okay, so how we will get? Here there is this representation will tell you that there is a double bond between C1 and C2 and C3 and C4. But between C2 and C3 there are no pi electrons. That is one nodal plane. Now we will see about psi 3 as well as psi 4. Psi 3 means pi star plus pi star. Okay, so what is pi star? Already I showed here. Okay, plus, minus, that is what? Minus, plus. Okay, plus, minus, minus, plus. Is there any bond between these two? Because opposite charges, no bond. Any bond between these two? No. Any bond between these two? No. Which tells us that the pi electrons are not fixed between the carbons. So how many nodal planes we got? 3 nodal planes we got. Next, psi 4, pi star minus pi star. What is first pi star? It is plus, minus, minus, plus. Minus, I already said to you, minus means you need to reverse the symbols, isn't it? So what we will get? Minus, plus, plus, minus. So because here there are two opposite charges, there is no bond here. Here also there is no bond. But between these two, because the same charges are there, a bond is there. Which tells us that the bond between C2, C3 is double bond. But with these there is only single bond. Means there are no pi electrons. So this clearly tells us that the resonance in 1,3-butadiene. 1,3-butadiene. But there is one more important point is always the electron excitations takes place from HOMO to LUMO. I will explain what is HOMO. HOMO means highest occupied molecular orbital. Highest occupied molecular orbital. Now if you observe these 4 levels, What are the occupied levels? Only these two, psi1, psi2. Among these two, which one is the highest occupied molecular orbital energy wise? This is the highest one. So that's why psi2 is the highest one. What is meant by LUMO? LUMO means lowest unoccupied molecular orbital. Unoccupied molecular orbital. So here what are the unoccupied states? These two. Among these two, which one is the lowest one? This is the lowest one. Always the electron excitations takes place between these two. Because here the energy gap is very less. Energy gap is very less. So that's why wavelength is more. Hence the lambda value will shift from 170 to 217. See here the electron excitations takes place from ground state pi of first ethylene to antibonding state of ethylene. Here a lot of energy gap is there. So that's why the wavelengths are shorter wavelengths, isn't it? When energy is more, wavelengths are shorter. So that's why we are getting this value at 170. But here the energy gap between these two is very less. Energy is less means wavelength is more. Hence we are getting the lambda max value at higher readings. So if we draw a graph writing absorbance on y-axis and this lambda max on x-axis, the graph is like this. For what? For this is for unconjugated alkenes like normal ethylene. Unconjugated alkenes. Now if you observe this one, this is for conjugated diene. Conjugated diene. So if you observe here the lambda max is here, but here the lambda max is shifted towards right side. Then one more interesting one is, for understanding purpose only, I am showing this as a dotted line. What is this dotted line? This is triene. Conjugated triene. Okay, like I already said to you, 135 hexatriene. So for conjugated triene, the lambda max is shifted more towards the right side. And one more interesting point you need to know here is, here even the absorbance reading also increased. Means we are parallelly we are observing both bathochromic shift as well as hyperchromic effect. In my previous video, I already said to you what is meant by hyperchromic effect. Means increase in the absorption. Okay. So once again, I will give you a brief explanation. Already we discussed about bathochromic, hypsochromic, hyperchromic, everything. Okay. But taking any one example, clearly how these lambda max are shifting towards right side or towards left side. So for that, first I am taking the unconjugated alkene like ethylene, whose lambda max is 170. If you took conjugated diene, shifting towards right side. If you are taking triene, more shifting towards right side. How it is happening? So for that, first I am taking the ground state of ethylene, which is having 2 pi electrons. This is another ground state of ethylene having 2 pi electrons. When these two are combined, there are two chances. In the two ways, these two will get combined. One is psi1 addition of these two, psi2 subtraction of these two. Suppose this, which is the excited state of this ethylene, which is the excited state of this ethylene, then these two will combine in two different ways, psi3 and psi4. According to pericyclic reactions, wave theory, I think in your previous semester you studied about these structures. Pi bonding is represented like this, antibonding is represented like this. How we got psi1 addition of these two? So this clearly tells us that there are no nodal planes. Happily bonds are there between C1 to C4. This tells us that the pi bond is between C1 and C2, C3 and C4. This tells us that pi electrons are not fixed between any carbons. This tells us that the pi bond is between C2 and C3. So by using these four combinations, we came to know that the resonance is there in 1,3-butadiene. How these electrons or transitions takes place in this conjugated diene, which is from HOMO to LUMO. Okay. So highest occupied molecular orbital, lowest molecular unoccupied molecular orbital, the energy gap is very less. Whenever energy is less, lambda values are more. So that's why lambda values are shifting more towards right side. The same thing we are showing in the form of spectra. Okay. In my next video, I will explain about Frank-Condon principle.